So this is the graphs that we got when we graphed when we graphed our torque for each of the cars with the distance, and the distance is just arc length. And when we recorded our measurements, we got torque, we got angle, and then we had the angle, and then we had to convert the angle into radians, and then we had to use the arc length formula of radius times radians equals arc length, and our radius was 0.5875, and so that's how we got distance, which is just arc length. So I graphed the two, and for the first mousetrap car, our slope was 23.9 newtons per meter. So that means that for every meter, the mousetrap car exerts a force of 23.9 newtons. And then for the second car, we got 26.4 newtons per meter, which means that for every meter the mousetrap car moved, for every meter, the force exerted on it by the spring was 26.4 newtons. Then for our third mousetrap car, our slope was 29.2 newtons per meters, which is saying that again, for every meter, there was a force of 29.2 newtons exerted on the mousetrap car. And then next, I took the integral of each of the following graphs, and integral is just pretty much area under the curve. And so this curve was actually a straight line. The data might have been a little off, but it ended up making a straight line. So the equation was y equals mx plus b. Now I'll explain that later. But for now, the integral under each of these, the first one was 0.2441 newtons per meter. And then that means that the area under this, wait, hold on. No, that's right. So the area under this graph, because we know that the area under the force, which is torque, and then the delta x, the area under that graph gives us total energy, because newtons times meters is joules. So the total energy we had was 0.2441 joules for the first mousetrap car. And then for the second mousetrap car, the total energy it had when it moved that distance was 0.3658 newtons times meters, which is just joules. And then for the third one, again, the integral was, or the area under the delta x, a force delta x graph was 0.2510 newtons times meters, or joules. So 0.2510 joules was the total energy in the third mousetrap car. 0.3658 was the total energy in the second one, and 0.2441 was the total energy in the third one. And then next we were supposed to find the amount of force in the car when the amount of kinetic energy in the car when the spring was pulled 180 degrees. So to turn that, we have to first turn it into radians. So 180 degrees is just pi radians, and then we multiply that by the radius so that we could have the arc length, or the distance, at 180 degrees. So we when I multiply pi times our radius, I get 0.05. I get 0.185. So 0.185 is the arc length when the spring is pulled 180 degrees. So now I'm just going to multiply 0.185 times each of our slopes in so that because the equation for torque is torque equals slope, which is 23.95 for the first one is 23.95 newtons times meters times arc length, which is in meters. So then the meters cancel out and we're left in newtons. So our first one, our equation is torque equals 23.95 newtons times meters times the arc length when the spring is pulled 180 degrees, or pi radians, which is 0.185. So we have 23.95 times 0.185, which gives us 4.43 meters, or newtons, sorry. So that means that for the first mousetrap car, when the spring was pulled 180 degrees, we had there was a force of 4.43 newtons exerted on the that's how much force was in the spring. And then for the second one, we have the slope 26 point, because the second one, the equation for torque is torque equals 26.42 newtons times meters times the arc length, and the arc length, as I said before, was 0.185. So I'm going to do 26.42 times 0.185, which gives me 4.8. So like the first one, for the second mousetrap car, it's 4.8 newtons, so there was a force of 4.8 newtons when the spring was pulled 180 degrees. And for the last one, the equation for torque is 29.23 newtons times meters times arc length. And our arc length, it's always going to be the same, so it's going to be 0.185, and that's because like when you pull the spring back, because it was the same spring, so when you pulled it back we had the same radius, so that's why our arc length is always going to be the same. So when I multiply this slope, the third slope, 29.23 times 0.185, I get 5.4, so that means there was a force of 5.4 newtons exerted when the mousetrap was pulled 180 degrees. That was the amount of force in the spring. So the third one had the most force at 180 degrees.